Hi all, once again welcome back to Ashkami. So today we have the sixth part of the question paper discussion that we were so far discussing regarding a recently conducted Kerala PSC exam. And if you're not going through the previous video, I've created a playlist in the channel. You can go through that. So you'll be getting all the videos. So without wasting much time, let's get started. So the first question of this video is question number 24 of the question paper, which is a question from organometallic chemistry, basically from the back bonding, a topic which is known as the back bonding. So in the options, you are provided with three different complexes, that is metal hexacarbonyls, and you're asked to arrange these complexes in the increasing order of CO bond strength. CO bond strength means CO stretching bone strength. Okay, so this is how you have to arrange. Now, in order to answer this question, we need to know some facts. That is, normally when a metal combines with ligand, say N ligand, to form a metal complex like MLN, what is actually taking place is that ligand will be electron rich species, that is it will be having either a negative charge or a lone pair of electron to donate, and metal will be having vacant d orbitals. Okay, so during the formation of the complex, electron from ligand is being transferred to the vacant orbital of the metal, and this leads to the formation of metal ligand coordinate bond. Right. So this is what is taking place during a complex formation. But for certain ligands like CO, Cn minus, NO plus, etc., they are known as pi acceptor ligand. Pi acceptor ligands are those ligands which have got vacant pi star anti-bonding molecular orbital, so that they can actually accept electron that is donated by the metal. So normally when the coordinate bond formation take place, electron from ligand is donated to metal. But certain ligands like a pi acceptor ligand like CO, Cn minus, NO plus, etc., they have got vacant pi star antibonding molecular orbital to which they can accept electron from the metal. So this is taking place only in the case of these types of ligand. So in these type of ligand, you can see that a electron from metal is back donated to ligand, and this is known as back bonding or back donation of electron. So this is a very important topic in organometallic chemistry. So as a result of this back bonding, normally we expect a metal ligand sigma bond that is formed by the donation of electron from ligand to metal. But if the ligand happens to be pi acceptor ligand like CO, Cn minus, NO plus, etc., then the ligand can accept electron from metal also, and that leads to the formation of a pi bond. That is, you can expect a metal ligand double bond character. That is, when this happens, it is seen that the um, the electron density of the metal will decrease, and moreover the metal ligand bond strength that will be increasing. Okay, so this leads to a strong metal ligand bond. Now we are asked to find out the order of CO bond strength, right? So in this case, it will be bonded like you will be having metal and you will be having CO. Okay, C triple bond O. Okay, so this is the uh, type of coordination that we expect. So when back bonding take place, what happens is that the electron will be donated to this CO. So as a result, when this CO, it gains electron, this bond will shift towards oxygen. So it leads to a situation like here a double bond will be formed and this will become O minus. So this is how the bone changes in the bone length or bone strength take place when back bonding is taking place. Okay, so when this happens, you can see that here you are having a triple bond, right? But when back bonding take place, that is converted into a double bond. So when you consider the bone strength in the case where there is no back bonding and there is back bonding, the bone strength is higher in the case of complexes where there is no back bonding. Okay, so two things are actually taking place. When back bonding is happening in a complex, the metal ligand bone strength is found to increase, but the CO's bone strength is found to decrease. So both the both the phenomenons are a type of synergy. They are having a synergetic effect on each other. So when back bonding back bonding is taking place, the metal ligand bond strength increases because that is converted from a single bond to a double bond. But the CO bond strength is found to decrease because that is converted from a triple bond to a double bond. Therefore, we can arrive at a conclusion that as back bonding increases, then CO bond strength decreases. Okay, so this is what is taking place. And when does this back bonding increases? So back bonding is actually possible when the electron is flowing from metal to ligand. And this is possible only when the metal is having enough electron to donate. That is, the metal should be in the low oxidation state. So back bonding has something to do with the oxidation state of metal. That is, when the oxidation state of the metal decreases, you can say that there is more back bonding. So therefore, we can also say that metal in low oxidation state leads to an increase in black bonding. So sorry, back bonding. So these are some related phenomena. So when metal is in low oxidation state, it leads to higher back bonding, and CO metal ligand bond strength increases, but CO bond strength decreases. Okay, so let's have a look at each option separately. Before that, if you want a further clarification of how the CO bond strength decreases when there is back bonding, I've already mentioned that during back bonding, the electron from metal is donated to the ligand. So when the ligand is happen to be pi acceptor ligand like COC and etc. In this particular case, when the electron is donated by the metal, I have said that the electron is entering the pi star antibonding molecular orbital, right? So you know that when you discuss about the molecular orbital diagram, it is normally seen that when the electron enters, or when the number of electrons in the antibonding orbital is higher, then bond strength is that is bond order is found to decrease. That is, if you have to find out bond order, that is half into number of bonding electron minus number of antibonding electrons. So when the number of antibonding electron increases, then bond strength is found to, or bond order is found to decrease. So that is why when the electron is donated by the metal to the ligand, the CO bond strength is found to decrease. So what can give a higher CO bond strength? When there is no metal ligand back bonding, then the CO bond strength is appreciable, or it is normal. But when there is back bonding, the CO bond strength will decrease. So you have to consider these three complexes separately. So we'll consider the vanadium complex first. VCO 6 times minus. So when you consider the oxidation state of vanadium, CO is a neutral ligand. Therefore, the oxidation state of vanadium is definitely -1 in this complex. So vanadium is having a configuration of 3d3 4s2. So when you are having vanadium in the -1 oxidation state, one more electron is there. Therefore, it is 3d4 4s2. On the whole, you are actually having 6 electrons, right? Now coming to CR CO 6 times. Here the chromium is in zero oxidation state, and the configuration of chromium is actually 3d5 4s1. Here also you are having 6 electrons. And in the case of manganese, CO 6 times plus, it is in the +1 oxidation state. That is, manganese is in the +1 oxidation state. The configuration of manganese is actually 3d5 4s2. So here one electron is less because it is in +1 oxidation state. Therefore, it will be 3d4 4s2. So it also corresponds to a total of 6 electrons. So you can see that these three species are having same number of electron, or they are isoelectronic species. So even though the metal is different, you are having the same ligand, carbon monoxide, and moreover they are isoelectronic species. So you can just look at the oxidation state of the metal to arrive at a conclusion where you can have higher back bonding. So you know that when the metal is in lower oxidation state, there is higher back bonding. So we'll just write down the order of back bonding. So when you go for the order of back bonding for this complex, it is like the one which is in higher oxidation state will be having higher back bonding. Sorry, lower back bonding. That is, the manganese complex will be definitely having the lower back bonding, followed by chromium in zero oxidation state, and vanadium is in the lowest oxidation state. Sorry, I have a bit confusion. So we are arranging it in the order of back bonding. So back bonding is possible when you are having a metal in the lower oxidation state. So here actually vanadium -1 is in the lower oxidation state, and chromium is in zero oxidation state, and manganese is in the +1 oxidation state. So this is the species, manganese 1 is the species which is in higher oxidation state. So there is no possibility for back bonding. So this is the order for back bonding. So this will be the order for metal, ligand, bond strength as well. So that is not asked in the question. In the question we are asked to arrange it is in the order of CO bond strength. So when back bonding increases, CO bond strength decreases. So the CO bond strength order will be the reverse of this one. That is, CO bond strength order will be lowest for vanadium -1, intermediate for chromium 0, and highest for manganese +1, where there is no possibility of back bonding because the metal is in higher oxidation state. In this question, +1 is not that higher oxidation state, but compared to the other two complex, manganese is in higher oxidation state. So back bonding is not possible. So this is the option that we have. This should be the correct option for this question. So when you compare the options, you can see that uh, this one, that is the first option, is the correct one. So this will correspond to the answer for this question. Okay, I hope you might have understood the question. If you find any difficulty in understanding, you can just give a comment in the comment box, and feel free to ask any doubts. So let's move on to the next one. The next question is a pretty easy question, and we have seen a similar question in this question paper itself before. So which of the following is not an organometallic compound? In that question, we were asked to find out which one was the organometallic compound. Here you are asked to find out which is not an organometallic compound, and you are provided with 4 different options: ferrocene, cisplatin, Caesar salt, and Gretna reagent. Again, you have to consider the minimum criterion for a complex or a compound to be organometallic is that it should have a metal carbon bond. So we'll analyze the structure of each option separately. When you consider ferrocene it is a bis-cyclopentadienyl complex of iron. So here you can see that this is a cyclopentadienyl ring and the iron atom is coordinated to the carbon atom of these two rings. Therefore, definitely it is having a metal carbon bond. So this is an organometallic compound. Now coming to cisplatin, it is an anti-cancer drug, and here you can see that there is no metal carbon bond, so this might be the correct option. Now coming to zezasol, which is also a platinum complex of different ligands. So here also you can see that the platinum is coordinated with the carbon atom. This is actually coordinating with the pi bonds of carbon atom of ethene. Therefore, this also satisfies the criteria for an organometallic compound. Now, coming to Grignard reagent, which is a very important synthetic reagent in organic chemistry, it is the general formula of Grignard reagent is RMgx, where R can be any alkyl group. So here also you can see that the magnesium metal is coordinated with the carbon atom of an alkane. So this also satisfies the simple criteria for an organometallic compound. So you can rule out this possibility. Therefore, from this, the one which is not an organometallic compound is definitely option B, which is cisplatin. Okay, so that's all for this question. So let's have the next one. The last question for this video is question number 26, which is about an important process in organometallic chemistry known as the Fischer-Tropsch process. So it is actually a process which is involved in the formation of hydrocarbon, and that too by making use of a mixture of carbon monoxide and hydrogen, which is known as the syn gas or synthesis gas. So this actually take place according to this equation, that is 2n plus 1 hydrogen plus NCO combines to form CnH2O H2n plus 2, which is the general formula of an alkane, plus NH2O. So by making use of this reaction, we can synthesize a number of hydrocarbons starting from the lower member to the higher member. So whatever we need, we can synthesize utilizing this Fischer-Tropsch process. Now coming to other option like alkene hydrogenation. So it's a reaction where you have a reduction of alkene to alkane. In alkene polymerization, n number of alkene unit will combine to form a polymer. And in hydroformylation, you can actually convert a alkene to a aldehyde by adding H2 and CO. So it is also a reaction which make use of hydrogen and carbon monoxide, but it is not the process that is involved in Fischer-Tropsch process. In Fischer-Tropsch process, we'll be using this synthesis gas to synthesize hydrocarbon. Therefore, the correct option for this question is option A, which is hydrocarbon formation. Okay, so that's all for this question. So with that, we have come to the end of this video. So if you like the video, please do subscribe and share. And I'll be coming soon with the next part of this video. So till then, take care and bye-bye.